Hello everyone, I'm Mengxing Tang from Imperial College London. Today I'm going to introduce to you super-resolution ultrasound imaging. Right, so first I will introduce image resolution in ultrasound, and then what is super-resolution, how we can achieve super-resolution, then in ultrasound super-resolution, how does it work? I will then introduce some past development in the past decade, and then some challenges and some recent advances. So in ultrasound imaging, we know that this is a transducer, and we can transmit a pulse, receive the echo, you can form an image. So with a resolution cell, if you can see my cursor, this is a resolution cell. Then it has actually three directions. So this is the lateral, the axial, and the elevational direction. The resolution, so you have resolution on all the three directions. So regarding the axial resolution, it is determined by the transmitted spatial pulse length. So this spatial pulse length is again determined by the transmitted center frequency and also the bandwidth of the system. For the lateral resolution and the elevational resolution, they are actually determined by how narrow the beam can focus in the lateral and in the elevational direction. And they are again determined by the transmission frequency, the aperture size. So the aperture size in elevational direction is this, and in lateral direction is this, and also the depth. So it's the depth of your point of interest. So in ultrasound imaging, we quite often use a number called F number, which is the depth of interest divided by the aperture size. And this, you can see, is important in determining the lateral and the elevational resolution. So for image spatial resolution, we know they have three dimensions, but how can we measure, even in any dimension, how can we measure the resolution? So first of all, I want to introduce the point spread function of an imaging system. So if you have a point target in here, very small, infinitely small point target, then when you do an image, you will never resolve this very, very small target. It will always, the image will be blurred. So this is your point spread function. And we know in ultrasound imaging, we have the kind of the radio frequency waves, and when you get the envelope, this is actually one direction, so one dimension of this 2D point spread function. So an image resolution, actually the spatial resolution, is defined by the minimum distance that the system can resolve between two spatial points. So if you look at, for example, in here, you have two small points, and you have the image of them, and when they are getting closer and closer, you can see at some point you won't be able to resolve. You won't be able to see there are 2 points within the image. So that minimum distance that you can still resolve that is defined as a image spatial resolution. So very often in practice, the full width half maximum of the point spread function. So if you have the point spread function in one dimension, the full width half maximum size is often used as an alternative measure of the spatial resolution. However, this one, the first one, is the most rigorous one. So I talked about the image resolution in 3 directions in ultrasound imaging. Then I talked about how you can measure spatial resolution. But what is super resolution? So when people talk about super resolution, they might mean very different things. So some may actually say super resolution when they actually means significantly improved resolution. But there's a more rigorous definition of super resolution. That is when the resolution achieved is beyond the so-called wave diffraction limit. So what is this wave diffraction limit? So this is a German physicist. He actually found this is in optics, in light. The light with wavelength lambda traveling in a medium with a refractive index n will have a minimum resolvable distance. So this is a wave diffraction limit, r, which is equal to lambda, which is the wavelength of the light, divided by 2 times the numerical aperture. So this numerical aperture is this refractive index n. So that is really the refractive index of the, so if you have the sensor aperture, you have the point, the target of interest, then this this medium here has a refractive index n, and also times sin theta is the numerical aperture, n times sin theta. And this theta is a half of the angle that the sensor collects signal from the point of interest. So if you think about if it's in the air for optical imaging, then the refractive index n is 1. And if you can increase your sensor aperture to infinitely large, very, very big aperture, then this theta will get close to 90 degrees. Then n times sin theta will be 1, right? So if this numerical aperture is 1, then actually the r is lambda over 2. Now half of a wavelength, so lambda over 2, is commonly used in wave-based imaging approaches. So this is not only optical imaging, but also ultrasound imaging as a diffraction limit, beyond which it is deemed super-resolution. Right. So we talked about what is a super-resolution in optics and in ultrasound, how we can measure it, but how can we achieve super-resolution? So, while some optical and ultrasound super-resolution studies have been reported in the past, the most notable advance in this area is this optical super-resolution fluorescence microscopy through this localization. So I'll introduce that in a second. So this is really where the idea of ultrasound super-resolution through localization originated from. Right. So first, then let's go through this optical super-resolution. So what I'm going to play is a video. And in here, in optics, what you see in here is a cell with a large number of fluorescence molecules in here. But actually, some kind of technique has been developed to be able to turn on and off these fluorescence molecules, individual fluorescence molecules, over time. So you can see it created some kind of blinking of these individual molecules. And in this case, if you see there is an individual molecule turned on and you see this blob, then you actually can localize it. By localization, I mean you can find, for example, the centroid of this, each of the blobs you detected, and then you record the center, the centroid of that blob. And then over time, you can accumulate this localization. And in the end, what you see in here on the left is a conventional diffraction limited images of this target. On the right is the super-resolution image of this target. So if you look at what they have done is about switching. So they use advanced optical technique to switch on and off these fluorescence molecules individually and sparsely, and then they localize them. This localization is the next step. They find the centroid of the individual fluorescence signals, and then they accumulate them over time. So this is actually the subject of the Nobel Prize in Chemistry in 2014. Right, so how actually exactly the super-resolution can be achieved through this localization? So here I just want to give you a little bit more explanation here. So if you look at conventional imaging, so say these dots, these are the kind of, we know they are the scatters with known location. When the scatters getting closer and closer, their image just their images will get closer and closer. So if you just take the look at the image, you can probably tell there are two scatters in here and maybe here, but gradually it's more difficult. And in here, you can't really tell, oh, there are two scatters in this image. However, in superlocalization-based approach, then here again, you have these two scatterers, you have their image totally almost all overlapping. But if you have a way to actually turn each one of the two scatterers on and off. So first you turn the left on, then you get an image, then you can localize it, find the centroid, so the center of this mass, and then you turn it off and turn the other one on, and then you can find the center of the second scatterer. And then by doing this, you can actually, by accumulating these two dots, you can separate these two scatterers. So the key to achieve super resolution through this localization approach is the prime information that only one point scatterer is in the image blob. So the scatterers has to be sparse and far apart at one time. And in this case, at one time, only one is switched on. And the second time, the first one is switched off, the second one is switched on. So such localization-based method takes advantage of the much higher precision in our ability to determine the center of the point spread function. Okay, so a super resolution image can be obtained by activating different scatterers and then accumulating the localization over time, right? So now I want to give you another example here. So in here, I'm drawing a road. And let's say I'm interested in this road. I want to image this road clearly. I'm interested in the, say, the transport structure, infrastructure of a city. So I might have a camera high up in the sky, and I want to see clearly image and resolve this road. Okay. Of course, I mean, there are buildings and structures surrounding this road. So there are cars on the road, okay? But if my camera is really high up in the sky and the image could be very blurred, the resolution might not be enough. So I will get a very low resolution image and the road is not clear, it's not resolvable. So how can I resolve this road? How can I get a super resolution image of this road? So one idea is actually we can image in the night. So when everything is dark, and then we pack the road with cars, but only turn on the headlights of, say, a couple of cars. So of course, I mean, if your camera is far away, you won't be able to resolve this car. But what you can see in the darkness is actually two glowing blobs, right? And then if we can localize the center, the centroid of these blobs, and then we know where the cars are, right? Although the image you get is much bigger than a car, but you know you actually can localize where the cars are. And then if we have the way to, for example, turn the headlights of those two cars off and turn the headlights on for another two cars, like in here and here, then we get another image with two such blobs. And again, we can localize their center. And then by just keep turning off and on the headlight of different cars and accumulating their centroids. And then in the end, we can generate a super resolution image of the road. Okay, so That's an example of how this super resolution works. But in the context of biomedical imaging, we'll say we're looking at a piece of tissue and you have the blood vessels in here. It's just like, for example, our road. They're just they're transporting blood and nutritions, and then you have the tissue in between. Yeah, that's how like you have buildings next to the road. In here, you have lots of tissues between the blood vessels. Okay, so we have tissue with embedded blood vessels, and the blood vessels are particularly of interest, especially both micro and the micro vessels, as their geometry and flow are closely related to the status of the surrounding tissue. Right? Example is like if, for example, if the early development of cancer is a so-called angiogenesis, where small vessels form. And a clinical system, a typical one, cannot really resolve blood vessels, small blood vessels, like below a few hundred of microns, although they can be very important and carry important informations. And another problem is that the surrounding tissue, although this is an optical image, and the surrounding tissue structure can give you much higher echo in ultrasound than the blood vessel. So to be able to do ultrasound super resolution of these vessels, what we need are really these three things. We need some agent within the vessel, like the cars on the road, and then we need to have a way to turn the surrounding tissue dark, right? And only the cars can be available and can be visible. And also we need a way to be able to switch on and off the individual agent. That's like turning on off the car's headlight. So for the first point, agent within the vessel, like the cars on the road, in ultrasound, we have microbubble contrast agent, which can be injected into the bloodstream, into the vessels intravenously. So that's tick. We also, the second, we need a way to turn the surrounding tissue dark. Actually, we do have such technology. We have varying filtering techniques. For example, the pulse inversion, or the singular value decomposition. These are the existing techniques which can remove the tissue background from the echo signal and only keep, for example, the contrast agent, the microbubble signal. And the third point is we need a way to be able to switch on and off individual agents. And this is a problem because actually the bubbles are always on, they're always visible to ultrasound. You don't have a way to keep them dark in the beginning and turn them on. However, we have flow. So in the blood vessel, actually the blood flows. So when bubbles are injected in the blood, they move with the blood flow. And when a bubble, so this is quite a key point, when a bubble moves between frames, it is as if the bubble in the previous position has been switched off and switched on as a new position. So basically, if you think about our previous example of cars on the road, then in the optical super resolution, it's like you pack the road with cars and then you turn on and off individual cars' headlights. But in here, what we do is on the road, we don't pack them with cars. We only have a few cars that's far apart and turn on their light. So we don't turn them off. They're always on, but we let them move. And then while they're moving, we can track these individual cars and localize their position. So that can also achieve this super localization. So let's show you some real data. So there is a microvessel in here, and this is actually the signal of a microbubble contrast agent. So when I play the video, you will see actually the flow is going from the right to the left, and you can see the signals appearing on the right and moving towards the left. And if you find this individual bubble signal and then you localize them, find the center of them, and accumulate them over time, you will generate this super resolution image of this vessel. And the diameter of your resulted image, when you measure it, corresponds to a 200 micron tube and correspond to what we know the diameter, the real diameter very well. Okay, so what do you need to do to generate this super resolution? This is a typical workflow in ultrasound. So USSR stands for ultrasound super resolution. So first step, you need to acquire the data. So you transmit pulse, receive echo, you get your data, right? And then the second part is about detecting this agent. It's like making the tissue surrounding structures dark, and then you can make the agent signal stand out. So that's a detection stage. And then there's the isolation stage where you can see some of the agents, the bubbles are separated, they are apart, but some of them are close together. And when they are close together, the signal mixed up. So when you look, you find the centroid of it, it will be in the wrong position. So we need to remove this and only find the isolated individual bubbles. And then you can, if you can see here, there are dots. So that is the centroiding. After the localization, we find the centroids of these signals. And then this is only one frame, but if you have multiple frames over time, then you can do some tracking of these bubbles as they move along the image. And then after accumulating this localization signal, you can generate a final image through this localization mapping. So, so there are a number of factors here I want to talk about. First stage acquisition. Some parameters are really important here. One is the frame rate. So if your frame rate is too low, then actually you could have problems in terms of tracking bubbles. And also the imaging sequences. You can have a B mode image. You can have, for example, this pulse inversion image that's specific to contrast agents. They will make a difference to your images. And also the imaging frequency. So if you use a very high frequency, your starting spatial resolution will be quite high. And that means you can actually get more, possibly more, because your resolution cell is much smaller. So you can actually get more bubbles, potentially more bubbles in a single image. But at higher frequency, many bubbles are not very active on the ultrasound, and your signal could be weaker. And another parameter is mechanical index, and we know that in bubble imaging, you always use lower mechanical index. If it's too high, you can pop the bubble. Another kind of parameters in this detection stage include also this pre-super resolution processing. So you can have this nonlinear filtering that is to remove the background tissue and make the agent stand out. SVD also can do similar things in terms of removing the background tissue, although it has some problems, inherent problems. And the denoising, sometimes the image can be quite noisy, especially when there's a high frequency image, when the bubble signal are quite weak. And also sometimes you do need this background subtraction to remove some structure that's not really bubble signal. And then you have this isolation of individual single bubbles. You need to localize them. You need some tracking methods. And there are actually lots of work going on in terms of improving each stage of this super resolution process. Another point I want make is that bubble concentration really matters. And if you have, I will talk this later more in detail, but if you have more bubbles, then you could have more localizations in a single frame that could speed up your super resolution process, but also it has a danger of bubble just mix up together. You can't isolate them and you can't track them well. Right, those are, so I talked about how this super resolution work and particularly ultrasound imaging. I will now give you some more early development, some examples of early developments. So these are studies where they show, so these two conference proceeding papers show the demonstrated the super localization of the bubble signal. And then later on in 2013, these two journal paper actually demonstrated the super resolution imaging by separating closely spaced structures. Right, this is actually the first in vivo demonstration of not only super resolution, but super resolved velocity mapping. So what you're looking at here, so this is actually the optical image of this structure. And this is the conventional ultrasound image. You can see it's quite blurred. But if you see here, when we put in the bubble and looking at the image over time, you actually can see these individual bubbles moving around this vessel. These are just like the cars moving around the road. If you can see this individual signal, you can localize them, then you can actually accumulate the localization and generate a super resolution image like this. And not only you can generate a super resolution image of the localization density, so the density of your number of localizations, but also you can, because the bubble, you can track them over time, then you can generate images of the flow directions and the images of the flow velocity. So this is another early development in rat brain super resolution image. When I play this video, you can see the accumulation of the signal over time in a part of the rat brain. And this is actually the final super resolution results in a single 2D plane. But actually you can do this in multiple 2D plane. And you can also display this in a kind of in a 3D way when you have this 3D information. And there are also a number of other studies. I just listed a few studies. They are just examples of this in vivo super resolution. This is a tumor model. These are the rabbit kidney. And this is actually a atherosclerotic model of visceral that's the microvessels that's on the vessel on the wall of aorta, abdominal aorta. Right. So this is another work we have done recently. So this is a lymph node. It's a rabbit lymph node. It's a quite small one, 4 millimeter roughly in diameter. And this is a B-mode image. This is a contrast image where you can see the microbubbles moving around in the microvasculature in these lymph nodes. And through localizing and accumulating this localization over time, you can generate a super resolution image of this lymph node microvasculature and also the super resolved velocity maps of this vasculature. And also, in this study, they demonstrated the resolution to be at least is on 30 microns by separating these two vessels. And the confidence these are two vessels because they also track the velocity, and you can see the color telling you that the flows are in opposite ways. Right. Not only this super resolution technology has been used in animal, in vivo, but also they already been trialed in human. So these are again just some first human application examples. So this is a results reported on human testicular lesion. And this is the report of the SuperResolution imaging on human breast cancer patient. And this is actually a report of SuperResolution on human lower limbs, the microvasculature in human limbs. Right, so these are really, I've showed you some example. It looks wonderful, but there are lots of challenges still exist. So one of the key challenge is the acquisition time. So at the moment, the acquisition time is quite long, typically tens of seconds. Some maybe a bit less, some even more if you're looking at 3D scanning. So bubble concentration actually matters because in here we want to localize these individual bubbles so they can't be very close. And if you use a lower concentration, they slow you down, right? Because you need to accumulate a sufficient number of this bubble signal. And also, since we need flow, it takes extra time to image slow flow in small vessel because you have to wait until the small vessel are perfused with these agents. Okay, another challenge is tissue motion. And so tissue always moves, especially if it takes time to acquire your data, tissue always move. And to correct this motion, particularly in here, when we're talking about spatial resolution in the level of tens of microns, then the tissue motion correction accuracy will have to be at least at that levels. And another challenge is tracking bubbles, particularly when the bubble concentration is high and the frame rate is low, how to best track these bubbles. That's another challenge. And the limitations with 2D imaging because you only achieve SuperResolution within the imaging plane, but in the elevational direction, you're still diffraction limited in resolution. And another problem with 2D imaging is when you have out of plane motion, then there's really very little you can do about it. So we need to develop 3D imaging technology, and that is what you're looking at here. So these are different studies on imaging, 3D SuperResolution imaging using different type of probes, customized, this is a kind of helmet-like probe, and this is a full 2D matrix array, this is a sparse array, and this is a row column array. You can see where for example, in this case, two kind of twisted microtubes, 200 microns each, can be spatially resolved by this 2D sparse array. Okay, so for the long acquisition time, what can we do? So one of the possibilities to increase bubble concentration, and then we can use some advanced image processing to deal with that. So potentially more bubbles can be detected at every frame. So the number of frames you need to generate this SuperResolution will be less, so less time required. But they need more robust signal processing, image processing to separate, isolate, and track this bubble signal. And if the bubble get too close, they can even physically interact. That will be another challenge. So a number of initial studies has been reported using the different techniques like deconvolution, sparsity-based image reconstruction, pattern recognition, machine learning algorithms to deal with a higher concentration situation. But here I am introducing to you another potential solution to this long acquisition time problem is to use this so-called phase change contrast agent. Because if you remember, I talked about in optical imaging, they can actually turn on and off this agent, but microbubbles cannot be turned on, they're always on. But this phase change contrast agent can be activated, they can be turned on. So I'm showing you the movies of if you look at initially these nano droplets, these are perfluorocarbon nano droplets. And in the beginning, they're not visible to light and also to sound. But after some ultrasound excitation, they pop into bubbles and they're visible to both the light and sound. So we actually have tried to use this to turn on and off this nano droplets to do super resolution. So this is our cross tube phantom, and these are the kind of every time we have a flash, that is another kind of a group of these droplets being turned off and on. And by detecting this signal and accumulating over time, then you can generate these super resolution images, comparing to these diffraction limited images and comparing to these optical images. And if you look at the resolution, you can see that it can separate structures that the conventional beam mode image cannot. And also more recently, we have developed this, so the previous, so this technique we call the acoustic wave sparsely activated localization microscopy, or we call also known as AWESOME. And so now we have developed if I move to the next slide, we developed a fast version of AWESOME by just actually changing the type of nano droplets, the phase change contrast agent we use. We can now use plane wave to activate and image them at the same time. So I'm going to play you a movie. Oops, sorry about this. If I apologize about this. Right, so you can see this is water, nothing is happening. For microbubbles, you see some signal and accumulation, then it stops because there is no bubble left in there. But when you have the nano droplets, when we turn them on and off, you see this kind of flashing signal, and then you can accumulate, you detect and accumulate the localization, and you can see even within 50 milliseconds, you generate already a pretty decent super resolution image. Right, so in this talk, what I have covered, I introduce resolution in ultrasound, what is super resolution, how we can achieve super resolution, and how this ultrasound super localization works, some development in the past decade, and some challenges and more recent advances. So I would like to acknowledge my collaborator Rob Exley and Chris Dunsby and all the group members who have contributed to the data I showed in this presentation. Thank you.